Okay, so very good evening to all. So in today's session, our plan is to introduce you people to the geospatial technologies. So as we have started with our mission to work on a multidisciplinary aspect, including quaternary geology, archaeology, anthropology, and the rock art sites. And as we know that the important aspect we have to cover is the spatial and temporal characteristics of the sites or the discoveries, whatever we are doing. So while considering this spatial and temporal relationship of anything what we are doing, which is related to any of the field what we are working, so the important aspect we have to always keep in our mind is that we should have a platform to compile these details and understand its potential. So the geospatial technologies plays a vital role in all these aspects. It's not only in our research, it is already there in all part of the our daily lives. It is already there. Like if you are moving there in a city, you look into the Google Maps, or when you go to a shop, and when you just come out of that shop, the Google will automatically ask you that, okay, what is your experience in that particular shop? Where did you enjoy that restaurant or not? What was the quality of the food? So we are constantly being tracked by these spatial technologies with a small gadget which is there in our pocket, the mobile phones. But when we actually trying to use this technology for our understanding on scientific understanding in geoarchaeological aspects, I can see that from the detailed registration form what you have filled, many people are using it, and I can see that also that many people have not yet started using it. So the point of discussion today, or my objective in doing this talk today, is to convince you people that these are all very simple technologies that anybody can use. There is no need to worry about it. It is simply doing some procedures and operating a computer application. So by operating these computer applications, we will be able to get a very good information that normally we may not be able to understand with our small data set, but putting it into the right context, reading it along with other aspects, we will be able to get a very detailed and beautiful story out of our study location or whatever information we are having in our hand. So it is not directly connected to any of this topic what we are having here, but it is a combination of everything. So if you are planning to make a career in this field, like in the prehistoric archaeology or prehistoric geoarchaeology or quaternary geology, or anything which is related to a spatial and temporal studies, I would suggest that if you have not yet started using a geospatial tool, you start it today itself. And this is not at all complicated. Anybody can learn this. And the people who are already using this technology in their studies at this moment, for them, this lecture may be a very basic one. Excuse me for that. But those who are not using it, try to understand the conceptual framework of this thing. Okay, so keep your mind open, try to understand what I am trying to convey the message, the conceptual framework of this thing. I'm not going anything in detail on any of these aspects, but I'm only trying to focus on the philosophical point of view, in the conceptual point of view, what these technologies are, where we can use this technology and how we can use the technology, and what are the points, some of the points that what make us demotivate in using this technology. They are basically the fundamental mistakes what we are doing in using this technology. I have seen many students, they start downloading the application like QGIS or ArcGIS, and then they start plotting it in the GIS, and then they will get worried, okay, that things are not going correctly. So for example, I have done a survey in somewhere in Uttar Pradesh, and I got some points. I came to my laboratory and I opened the application QGIS, and I plotted those points in the map. But when I plot these points, the points are actually going into Arabian Sea or Indian Ocean or in some other country. So then people like, oh my God, the data set is not correct. And sometimes I see that people getting a point very accurately using a GPS. And when they come down to the laboratory and plot it in the GIS application, and then they realize that it was a point which I took very close to a river, but the point now when I plot it, it is falling far away from the river. So there is a difference in the point. So basically all these things are because of doing some things which are not correct. So the system is perfectly working, but we are not aware about that what actually is happening in the backend, how these things are operating. So the objective of today's lecture is to bring to your attention that okay, these are the things we have to keep in mind while using this technology. And during this 1 month period, because you know that I already told you people, I haven't explored Odisha yet. This would be my first visit to an Odisha archaeological site. So I am planning to do a geospatial analysis for these sites where we are planning to visit. So I am going to do one by one the processes or what routine processes what I do, and everyone will have their own different methods to do. It is not necessary that whatever methods I am doing, you have to do it as such and you have to replicate it. You may have a different methods to do. It is nothing to do with, ultimately we are all worried about that, the context what we are getting from this area. So I am planning to do these things in the coming 2-3 weeks. So I'll be doing it one by one. So what I am planning is that whenever I do these things, I will keep you updated about, okay, so I am doing this aspect and this is what the tutorial. And here I would not be giving you a detailed lecture on all that aspects. Rather, I will try to find out some tutorials which are available in YouTube, and I will give you that tutorial and then I will tell you to follow this process. So this would be a self-learning process, that if I take all the lectures on doing these things and trying to teach you, it is going to be a very lengthy process. We may not have that much time to cover in this particular session at this point, and this would be open for all the people who are interested to do that. So what you have to do is, you have to keep an eye on the Google Classroom. Whenever I do a process, like if I am downloading some data, if I'm downloading a spatial data of an SRTM data, so I'll be putting up a tutorial and you can follow this tutorial. And before that, I may take few sessions or a few things to installing the software and trying to understand the software. There, the biggest trouble what I'm having in front of me is at this moment, I use the software called ArcGIS for all my GIS work, and I have a licensed version of ArcGIS. And it may not be possible for all of you to get a licensed version of ArcGIS at your place. Those who are having an ArcGIS, it will be better because that is a very powerful software to use, and it will be much easy compared to the open source softwares. So I can suggest you that though I am using ArcGIS, I have used QGIS, that is a open source software for doing the same things. It is equally powerful like ArcGIS, but only thing with the QGIS is it's an open source. There are constantly modifications going on, new tools are coming in, the workflows are changing every day. So sometimes we get little bit irritated. Sometimes some of the functions may not work exactly the way as we want. But in the commercial softwares like in ArcGIS, that difficulties are not there. It will keep on working as the way it is working. But QGIS sometimes create troubles. And comparing to the price, if you are going for an ArcGIS personal license for an year, it will cost around 10,000 rupees for an year license. So for ArcGIS Pro, whereas QGIS it is free. So while using these techniques or studying these techniques, I will recommend that you don't have to go for a cracked version. Rather, you can go for a QGIS freeware version and start using it. So I will be putting both the things in the classrooms whenever I'm doing something. These are the tutorials. So start or try to follow that sequence, because the software what we are using, even the QGIS or NAVGIS, they both are so powerful tools. We can do so many different things. I personally believe that I only utilize it for around 5% of its actual functionalities. That is what I personally believe. I started using a software called MapInfo some years back, around 2006, and then slowly I converted to this ArcGIS, and almost last 18-20 years I am using these softwares, but still I believe I'm not using it very extensively, because this is only one tool along with many other tools I am using, and I'm not a regular user of ArcGIS or any softwares. I'm using only when it needed. Like now I need to study the Odisha geomorphology, Odisha river pattern, where we should go for an excavation or exploration, on which sites we have to see to understand the geology of that area. So where would be the possibilities of getting an archaeological sites, if there is any reported site in that region, and where are those reported sites? If we have a reported site there, what is the relation of that sites with the local geology? Like many questions I have in my mind at this moment. Okay, so this is how we start, because this is the first time I'm going to explore this region. So I have my own questions in my mind. I'll be trying to look into that questions using these techniques, and I wish that you follow that path along with me, so you will get an experience on doing that. At any point of time, if you have any difficulty, we can discuss at that point in one-to-one discussions through a video chat, or you can talk over a phone, or we can do something to solve that problem. But you have to keep following the processes. So that is what I am actually planning now. I'll keep you posted whenever I do these things. So try to follow those things, and take it granted, if you are thinking about a career in archaeology, geoarchaeology, quaternary sciences, without these techniques, without having these tools, it will be very difficult. We should be able to show what we are doing in the spatio-temporal scale by using these technologies. There are free tools available, there are commercial tools available. Some of you people who are having a facility or licensed versions of ArcGIS, prefer start doing it. If you don't have, don't worry, go for QGIS. They are all both very powerful. Only thing, I used it so many years back, the QGIS. These days they have changed a lot of in the interface, so I'll have to struggle to find out the functionality sometime, because I don't use it very frequently, or I haven't used it for many years, but I still be able to find out the things if you are actually stuck with some trouble. So that I can give you, that help I can give you in case if you stuck at any point. But otherwise, the internet's resources, the YouTube videos, tutorials, we have tremendous tutorials available for that. Only thing we should know that which keyword we have to search and which tutorial we have to follow, and everything we can do by following the tutorials. Very beautiful videos are there. So what we are lacking at this moment, those who are not using this technology, that is a conceptual framework of this technology, what these functionalities are, how these things are operating. So today's session, I'm focusing on that, bringing you into that platform where these functionalities and the philosophical background of these things I'm trying to explain to you people. Okay, so in the point of our discussion, the topic wise, this is going to be applicable to any. If you are having a rock art sites, it is important where the rock art sites are, which elevation they are, what is the context of these sites, where is any nearby river or not, if you have any nearby forest or not, which is in an elevated surface or in a lower land. Many things can be answered by using this technology. Let's come to the geospatial technologies, what we are basically interested in as a geoarchaeologist or the people who are working on spatial temporal details. The first one and the foremost important one comes in remote sensing. Okay, so remote sensing is nothing but it is studying something remotely. I'll come to that. Then the second aspect which comes into the geographical information system, that is GIS. And the third one, it is the GPS, Global Positioning System. These are the three technologies which is existing as of today, and we are dependent on this. And out of these three, if ask me which one is the most important, I will say that the remote sensing is the most important aspects that everyone should be exploring. We should start exploring the remote sensing technologies. I'll come to that why it is. And GIS is the very basic one that anybody in the 7th standard, those who can move a mouse and they use a computer, start and open a software, can use the GIS platform. And GPS that we are using every day, it is our day-to-day life. Whenever you go to any place, you are using GPS, and the mobiles have GPS receivers. So as of today, we are all using it continuously. Only thing that the accuracy of these points may be different at this point. What you are using a handheld GPS may have a less resolution compared to the other commercial GPSs, which give you a much better resolution data. But at this point, whoever is working in this field, when we are in the field, we are dependent on either a handheld GPS or our mobile phones. So that is to identify where we are standing. And GIS is to plot that points into a software. And remote sensing is the basic, that is to understand the context. So remote sensing can give you much more details and much more information about your site and its context and its geological aspects and its historical aspects in geospatial studies. So remote sensing is the most important thing. GIS is the very basic thing. GPS is our day-to-day activity. We are doing it already. So let us take one by one. What is this remote sensing? When you say remote sensing, this is nothing complicated at all. It is nothing difficult at all. What is it? It is simply identifying or understanding any object without being in touch with that. Okay, that is called remote sensing. So I am not touching anything. I'm not going close to anything. I'm not in the close proximity or something. I'm at far distance to that. Then I am trying to understand that. That is remote sensing. So there is always between the observer or the person who is trying to sense remotely and the object, there would be a medium which is transmitting the signals through which, and we are trying to understand it. So that is what we call it is the remote sensing. Now, do we call this is remote sensing? Technically, yes. Technically, what they are doing, they are trying to understand something, looking at a binocular, and what they are trying to do, they are trying to understand where are they, how much far the object is, what is the shape of the object, whether they have changed in the past. So we have a temporal details. What is it looking right now? If it was something same in the past or not, whether there is some mix of object or not. So many things. Looking from this, we can identify. So technically speaking, even if you are standing, if you are taking a big ladder, going to the surface and looking at the going to the subsurface and looking to the surface and taking a photograph, we are technically doing remote sensing. I have never seen anybody specifying that, okay, every remote sensing has to be from a height of around 5 kilometers, 6 kilometers, or using a Landsat image or something. But no, it is not like that. It can be anything which is capturing the object without being in contact with that. It comes under the definition of remote sensing. But when we, most of the time, when we talk about remote sensing, we are talking about which is much in the higher level. And these things evolved over a period of time, starting from around 1859. So people started looking at the object from the height and they started clicking photographs. And it was widely used in different time frames in the World War time, and that all different phases. They have widely used the movement of people, where are the boundaries, what are they doing. So this is how the things started evolving in around 1859. And then there were the invention of the aeroplane. Then the people started capturing the images from the aeroplane. And finally, we come to the actual remote sensing that we are using right now, that is using the satellite images. So satellite images, again the same thing. Only thing, the satellite sensors are much above. So there is a say object which is continuously monitoring, which is moving across our globe, and it is keep on capturing the images. And if you see the history of these remote sensing images, when the time when I was doing PhD, like in the years like 2006 and 7, we people were so lucky to get a remote sensing image. Like if you were able to get a image of the river system, the remote sensing image, that too a printed one, and then we are so happy that okay, we got a remote sensing database. And it was not easy to get the data until the point when 2006, when I was doing PhD, or when the people of that time, then these people were doing PhD, the data of the spatial data was like something lottery for us. If somebody is having a remote sensing image of that region, then we were so happy. We were like, oh my God, we got so many things to find out from that, because these things were not free of cost. It is not available free of cost. But today in 2024, when I am sitting here, the entire remote sensed images are freely available to anybody in this world. That too, we can get a 30-meter resolution. That means we have one single pixel, or one single pixel size, which is 30 meter. We have one database. That is more than enough for most of the studies what we are doing. That is more than enough means that is very, very, very much more than enough for what most of the studies what we are doing at this moment. The things are very simple. What it is doing, there is a satellite which is there on the outer space, on the space which is rotating, and there is energy source. Normally all these satellites, they are not using any energy source. They are using the energy source as sun, and sun is continuously transmitting the energy, what we call it as the electromagnetic spectrum. And in that electromagnetic spectrum, we are capable to see or visualize the visible band. That's a particular wavelength, and rest of the things we are not able to identify. But the remote sensing satellites, what they are using, they are capable to get these signatures reflecting back from the surface. They identify that signature, they do record that, and then they transfer it into the surface through an image. So technically, and the very simple words, if we say this is a photograph, but the photograph is not like the photograph what we see, because we as a human, or our camera what we are using, that camera has a limitation of using only within the visible range. Visible range is that the white light. So if you are switching on the light which is coming, that is a particular wavelength. Beyond the wavelength, it is not producing any electromagnetic spectrum. So when these satellites are using, they are capable to take little more wider wavelength, and that is the benefit where what the things we are not able to see with our naked eye can be detected using the remote sensing data. That is the most important, beautiful part of it. Okay, so that is the remote sensing simply. So there is a source of light which goes to the surface, reflecting back, and the reflected things are recorded by a sensor, and sensors are aligned in different sectors. It is not one single sector. There are 1, 2, 3, 4, 5, 6, 7, 8 or 9 different sensors are kept. So when it is capturing one single location, one single square area in the surface, and when it is recording, they are recording 8 different parameters of that area and combining it together and giving us a layer of 8 different parameters. So whenever we download a remote sensing data from any web sources, what we are getting is not a single image like what we are printing from a studio. It is a layer. It's a layer by layer. We get 7 or 8 or 9 or 11 layers. So each layer are defined to a particular wavelength. So when you come to the wavelength, what is this wavelength? So these are the functionalities of remote sensing. What is the wavelength? There are different wavelengths. So sun has an energy range, larger energy range. It produces this energy. As I said, our eyes are not capable to find out everything, identify everything. We have limitations. We have a very shallow, small spectrum, which is our sensor. Our eyes are also same. These are all sensors. So eyes have a limitation of identifying this much wavelength. So we are able to identify violet, indigo, blue, green, yellow, orange, and red. So this is different wavelengths. And if you go for a printer, the printer is not even have this many different colors. They are only either yellow, green, magenta, or they are RGB, red, green, and blue. So these three colors are producing most of our printers, okay, print products. But that is, our eyes are able to detect more than that. So we have different variations. But our remote sensing sensors are almost capable to produce or capture the information double or almost triple the wavelengths what we can identify with our naked eye. Okay, so this is the spectrum our eyes can identify. So when the light falls on some objects, I can see the object whether it is blue or green or red or black, or if it is black, that means it is absorbing everything. If it is red, that means it absorbing everything except red. That is why the red wavelength comes to our eye. We are able to identify, okay, this object is red color. So when I see a blue object, that means the white light falls on the surface. It reflects all the other wavelengths except the blue. So my eyes are detecting, then I know, okay, this is blue in color. But when it comes to the remote sensing, these people are capable to identify in 9 basic branches. This is Landsat 8 what I'm talking about, but that is what basically I use in most of the studies. Landsat 8 gives a very good resolution, that is 30-meter resolution, freely available database. Download it and use it. Okay, so what we are going to get when I'm going to download, I will get around 11 bands. Here I have plotted only 11 different layers. So each tile which covers a square tile which covers an area, and there when I download, it goes into 1 GB, almost 1 GB single file. Don't worry about this 1 GB file. This maybe you look like a large file, but when you download this, you basically use only from the 2, 3, 4, 5, 6, and 7. These 7 bands are what we are using in most of the cases. And out of the 7 bands, 2, 3, 4, these are the ranges what human eyes can also detect. So the Google Earth, what we are seeing, that is basically a combination of these 2, 3, and 4, and 5 bands only. They are not using the shortwave, infrared, or other bands. So this shortwave, near infrared, these bands, the reflectance have different property of different materials. Soil will have a different property. The vegetation will have a different property. Different vegetation will have different property. Dry leaves will have a different reflectance, and the wet leaves will have a different reflectance. The agricultural land will have a agricultural vegetation will have a different reflectance. So there are so many different vegetation, different differences we can find out from this, and we don't have to worry about all that also. Even like when you are trying to study about the water bodies, for example, okay, so there are people already doing research on this kind of things, in what band which kind of water will have highest reflectance, and they also have produced equations. For example, there is an equation called NDVI, normalized differential vegetation index, across the globe people uses. So that is simply the ratio of few bands. They take one band, the value, for example, they get 100, then they minus the other value, then they get an equation, and they divide that with another value, then they get a single value. So when they get that single value, they are using 2 to 4 bands in that. So this research we are not doing. We don't have to do that. We have to just see that what equation they have proposed, and based on that equation, if I want to characterize the vegetation in that region, how many different bands I need. So take that band. Each band will have millions of pixels. Each pixel will have one value. So take that one value from one pixel, same corresponding pixel from the another layer or the another band. You subtract or minus or multiply or divide or whatever equation says, you do that, and you say that the software, okay, now you do this thing for the entire million pixels. Software will do it. We don't have to worry. We just need to tell that equation, like what we are doing in the Excel. If you have to divide two values, you put it in the one cell and put another value in the another cell, and then you write an equation equal to this divided by this. Then you double click or pull it down. What it is doing, it is calculating for the entire thing. Same thing the softwares are doing. Okay, so the theoretical background of these things we don't have to worry about, because people are already doing it. They have produced equations, so we have that equations in our hand. So we need to just understand, okay, what bands they are using in the equation. So for example, if they are giving an equation band 5 minus band 6, divided by band 5 plus band 6. It gives a single value, and this single value is an indication of soil characteristics. If the soil is hard, then we will get a higher value. If the soil is soft, then we get a smaller value. What you have to do, you have to go to the software and write down. There is a calculator, there is a function called the raster calculator. Go to the raster calculator, give the equation band 5 minus band 4 divided by band 4 plus band 5. Then you press enter, so that will calculate for the entire million pixel what you are having in that region, or what you are doing in that region. So very simple process. Only thing what we need to do, the conceptual clarity of this thing. Why we are using this NDVI value, or why we are using this soil index, why we are using this particular index. Only that conceptual theoretical background we have to study from a remote sensing literature, then you apply it. Like recently I did an exercise we did a couple of exercises. We did an exercise with one of the students from Deccan College. He wanted to identify, because his region, what he was studying, which was all in the forested region. So he was looking for the exposures, basically where from the soils are eroding. Okay, this is in the Bihar. So he was looking for where is the soils are eroding out. So that would be the regions, all the areas where there is a chance of the stone tools also will erode out. So he wanted to do an exercise. We were discussing casually what we can do. Then he started looking into it, and then he found out there is something called soil erosion equation. Enhanced soil erosion equation. So that equation was proposed by somebody to identify or locate the regions, those regions having highest soil erosion. So he applied that same technique here in his region, and he come down to around 7 to 8 locations, which he identified. Okay, this 7 to 8 regions have a high amount of soil erosion. Okay, and that soil erosion is not only depend on the soil, the remote sensing data is also depend on the slope, the kind of the soil density. Many parameters are there. So he tried to find out all that parameters, and then he come down to around 12 or 13 locations in that region, his study area, where the soils are eroding very fastly. And then he physically go to that sites and visit those sites, and out of these sites, around 80% he could collect stone tools. Okay, so it doesn't mean that other sites doesn't have stone tools. Other sites also may have stone tools, but this reduced a lot of work. If you are a 50 by 50 square kilometer region, and if you have to do the entire region doing ground survey and find out this location, it is practically very difficult. So we have to use this kind of logical reasonings, and these techniques are capable to use such kind of logical reasonings, which will help us to reduce our mechanical work or the field work, because field work is a costly affair. If you are going for a field work in one place, the worst thing what we can do is that we can go by taking a bicycle and do yourself the field survey, but it is going to be so lengthy. But if you are hiring a vehicle, staying somewhere there in a hotel or in a rented house, or if you are having food from outside, it is going to be a very costly affair. And these costly things, at this moment, neither you are able to manage, we are not able to manage. We are also having difficulty in getting funds for this kind of works. So we have to optimize our resources. With limited resources, we have to come out with better results. And if we have to come out with better results, we have to use this kind of things and reason out into small regions. And you only go to those regions and identify. And these identifications are not random. You understand, these identifications or these things what we are doing are not random. This is a logical reasoning what we are applying to come down to these 16 locations. It has a science behind it, and it is a proven science which is used across the globe by different people. Okay, so that is the point at this moment, where we have all these facilities. Database is free available, software is free to use. Only thing, we need to start using it. So I'll get through that process also, how to use that, and we'll go on doing it. And this is all remote sensing textbooks will have this signature curve. This is nothing but which only shows in a wavelength. For example, this 0.4 micrometer to 2.4 micrometer. Where is it? 0.4 micrometer to 2.4 micrometer. That is 0.4 is somewhere coming here to 2.4. That is the highest visible range, highest range in the remote sensing. So this range to this range, so it covers most of the part of the visible range and then the other part. So here, what is the reflectance? What is the reflectance means? Reflect means when the sunlight or the electromagnetic spectrum or the radiation falls on an object, how much it is reflecting. Okay, so how much it is reflecting is what they are measuring. So the reflectance of these objects are given for the different. Water will have a highest reflectance on this range. After that, water will not reflect any. So all the wavelengths beyond that, which is going to be absorbed by the water. So there would not be any different color which is reflecting. That is what the reason when we see the water from the surface, we see the water in blue color. You must have studied it in the science classes in the school levels, that the water sees in blue color because it reflects blue in the range. In that range it reflects, so it gets blue color. But this is the typical pure water signature what you see here. But if the water is impure, if the water is contaminated with pollutants, then there would be different peaks we will be getting, and people have done research on that also, and based on that they are able to identify which kind of bacteria is there in the water by using the remote sensing studies. So there are many advanced things going on. And the same way, if you are going to the soil will have a reflectance from all these ranges, and the vegetation will also have all these ranges. But then when we see, we can identify there is one particular range, this is around 1.5 micrometer. The differences or the distances between these two curves are very, very maximum. So at this range, at this band, if you take the difference between these two regions, then we will be able to understand whether this area is soil dominated or water dominated. So, okay, because see, ultimately in no area is only soil, no area is only vegetable, no area is only water, unless and until you are in a sea or ocean, it's purely water. Otherwise, we'll have all these different things combined. For example, if you are studying somewhere in a forest, so forest will have vegetation. At the same time, it will have soil also below that. So the reflectance what you are going to get will have all these things combined. So this kind of pure complete signatures we may not get in the actual remote sensing data, where we'll get a combined everything. So we need to identify that which bandwidth I have to study. The same way what we did an exercise recently from the Konkan region, because where we were having laterites, different varieties of laterites. So we wanted to see that, okay, whether these laterites are all of same category or not. So what we did when we tried to look into the remote sensing data and try to find this kind of reflectance curve from the remote sensing data in different bands, we got some curves, but it was very, very hazy. We are not able to identify that. Then what we did, we go to the field, we collected around 12 different laterite samples, we make it into powder, and the same sensors what we are using are available in the instrument form also. So I have a laboratory which can measure the reflectance under a laboratory condition. So make powder of this, and then we put this under the microscope, and then we measured the laterite signature of that powder and made this kind of curves. And from that curve, we identified, okay, this particular wavelength, this laterite is showing a maximum reflectance, and this particular wavelength and another rock types is having a maximum reflectance. So based on that, we prepared our own indices or the equation, like I was talking about the NDVA, normalized differential vegetation equation, that is prepared by some other scientists, but laterites nobody has worked, so we had to make our own equation for that particular location. So that also we can do. Okay, so these are the things we can do, and this all depending upon the user, what kind of users we are having, what kind of requirements we are having. So this database or exploring this data or using this database is something very, very, very important and have a huge potential in any of the area what we are planning to work in. So these are some of the old images, not in the recent ones. This was some years back when I was studying the Tapi River, and where we are making. So this is not what you are seeing in the Google Earth. Though you feel that, okay, it is same like Google Earth, it is not Google Earth, because Google Earth you cannot differentiate or you cannot make a map of, if for example in the remote sensing data I can write another equation, okay, now you make a shape file or make a curve of all the regions where these greens are eating. So these greens are basically the cultivated land. So these all are cultivated land, and this is barren land, for example. So I can make, and what we see here, there are some clouds because there are two different tiles. There are some clouds also that it was not so much important for us to understand in detail, but it was just a general database. So if I need to measure that how much area is covered with this particular color, this green color, and I know that it is a vegetation, and I can calculate that from this software. I can just write a single code, or not a code, a single equation, and go to the raster calculator and write, okay, now you calculate the entire region where it is green and give me the area which is covered, and make a polygon or a map only that layer. So I can export that single layer and use it in quantifying the things. Okay, so there are many such possibilities of using this, and we are using it extensively, but still I believe that I'm only using around 5% of this. And recently there are new technology coming up that we call it as the Google Earth Engine. Okay, for example, here this image is captured in 2024. For example, this image what I'm studying here is 2024 image. But if you go to the database, we are having database from 1984 onwards. So millions of images of this same area is being captured by different countries. Landsat is one. Likewise, Russia have different satellites, China have different satellites, different people have different satellites. So only USGS made it available free of cost, 30-meter resolution, anybody can download. So we are using it. But this database is already there with all countries. Different countries will have different database, different resolution, 5-meter resolution, 2-meter resolution, 1 centimeter resolution, different databases are available. So these all databases are available. So Google has come up with a new technology. It is not Google Earth. This is called Google Earth Engine, but it is still in the developing stage. You can still go and see the Google Earth Engine in the web, where if you find out there are number of areas they have already mapped, and they call it is time-lapse analysis. What they are doing? They are capable to monitor or prepare a movie out of each of its location during the last 40 years. Changes. Like if you go to the Dubai city and you find out the Google Earth Engine portal, just Google it out, the Google Earth Engine, you will go to a portal where you see the time lapse, and there are different locations they have already produced, sample database is ready. And if you just click Dubai and you see, they will properly show you in the last 40 years this area developed in how many stages and how they were increasing, and how the seas were moving, and the Koshi River migration. Everything is available. It's gone much beyond that what we are talking about right now. And we are already working with computer engineering students of my department. We are trying to train them to use this kind of technologies, and we may come out with something in the near future. We did a small exercise in Narmada already, but we are planning to do that also. Okay, so that is the next level. But by the time you people study remote sensing, this may not be the technology people may be using. I'm sure in the next 5 years that would be a important technology that people will be starting. And if any of you have little expertise or little knowledge about the Python language, then that area is something that you should start exploring today itself. You don't have to worry about remote sensing. You start exploring Google Earth Engine. Forget about remote sensing. That will be more rewarding for you. Okay, so that is about the remote sensing. I hope I'm clear about the conceptual framework of this remote sensing. Now the practical aspects will come to that later.
Thank you.
Okay, now coming to the geographical information system. Trust me, geographical information system is nothing. If you have used any softwares like CorelDRAW, Photoshop, if you have used Adobe Illustrator, if you have used Canva, if you have used any of the digital platforms where you can produce some images, or you can draw something, AutoCAD, any of them you are used, this is same like that only. This is simply a software. It's nothing more than that, a software. But it is a very powerful software, because if you are using a CorelDRAW, you can draw the lines, but if you export that line and open it in Google Earth, it will not go and fall in the exact location where you are drawing it. Where in the geographical information system, along with that, we have one more dimension attached, that is the latitude, longitude parameters of that location. So the geographical information system is nothing but a software. It is a collection of computer hardware, software, and geographical data for capturing. This is the definition. Don't go for the definition. It is nothing but a software which is capable to understand the location specific data. Like today, when you capture an image in your mobile phone, it asks you whether you want to geotag it. What it is happening when you geotag it, that photograph, if you upload that photograph into your Google Photos, and when you open the Google Map will show that, okay, you took this photograph in this location. Why is it happening? Because that geotagging, the remote, the GPS receiver which is there in your software or in the camera is actually attaching one more dimension to that. So that is the reason that image exactly goes into the location where you captured that photograph. That is what only which is doing here in this software. This software is capable to understand the latitude and longitude of that region, and they are capable to convert and play it within different things. But when it comes to the playing it within, along with that, you can make a number of statistical analysis also here. We can identify that, okay, there is one location in this map. You tell me what are the areas which is 100 kilometers around this area, around this point, and you also tell me out of this all locations how many are buildings and how many telephone posts are there and how many water bodies are there in the 100 meter from this location. So you have to have a database which also have the locations of the buildings, the locations of the water bodies, the locations of what I asked the vegetation, whatever parameter. So that layer is already there in the database. Then the software is capable to identify all that things and generate a new layer and tell you only those questions what you ask to that software. So for that, what we need is that different layers, and these softwares are capable to produce that different layers and organize it properly, and whenever you ask, they are capable to get the things as you ask them. So you can generate different queries to the software and they can produce and give it in the beautiful map format from this software. That is what this software does. So in our point, this is simply, what is it? It's a software, and this software, these are all textbook images which is available there in the market. They will be making things very complicated, but technically nothing, which is a software. Whatever data you give to the software will ask you what is this data and where is this data from, and then it will tag that latitude, longitude, and then it will add to that point and it will all store. At the point when you need this data, it will give you that data back as the way you want, and it will produce some beautiful maps or the graphs or something, whatever way you need. The software and hardware, if you see this image, this is very technically very funny for me. The hardware, what you're doing is a computer we need people to operate the computer because computer cannot operate themselves. Then we need people, the users we need, they are doing it. Then you need data. This is the most important aspect, and this is the most important aspect, data and the approach. And what data you want to use, what approach you are using. Every individual who is using these platforms will have different protocol, different way of using it. For example, if you ask me that what data I use in this, I use the database from the river drainage maps. I use the geological maps. I use the archaeological sites. I use the topography. And the best part of all this is all this data are free to use. I can go to the website, download a digital elevation model. It will give me the entire globe, technically, the elevation models. What is this elevation model? It's again like a image, but each image will show me millions of pixels, and each pixels will show me a number, and that number is the elevation of that particular location. So if it is a hill, it will give me 200 meters. If it is a valley, it will give me 90 meters. So this database are all freely available. It's free to download. If you want to download the Indian geographic maps, you can download. If you want to download the Indian geological map, you can download. If you want to download the Indian river basins map, you can download. If you want the archaeological sites, it's developing. Geological Survey of India is doing it. It has not yet completed, but we have already done it. We have around 1,500 or 2,400 archaeological sites, prehistoric archaeological sites across the Indian subcontinent. We mapped it, we identified it, but still in the primitive stage. And those people who are actively doing these things, we are planning to use your help in making those database better and better. And the world is now doing this kind of database and collective research. There are a number of different. Neotoma is a database that is the European people are doing and collecting the entire globe's paleoclimatic database, and they are making a global data set. The road network is done by a German scientist, and this is basically the database of the archaeological sites. And the worst part is that from India there are only 5 or 6 archaeological sites are there in the road database. So we need to, but the problem is that I'll tell you our experience. When we started collecting the database of all reported archaeological sites from Indian subcontinent, the prehistoric sites particularly, and we tried to map those sites in the Indian map. And the problems what you have faced. Number one, most of the sites names given are simply the local names of the site, and they have multiple spellings to represent that name. For example, if I say the location name Kutch have different spellings. So when you see one literature, they have one different spelling. One literature, they have another spelling. And many of the sites, they don't even have specify the locations of the sites. They just simply say, okay, we got the Paleolithic tool 50 meters away from the river side. So 50 meters away from the river, there is no latitude, longitude attached to that. There is no points attached to that. So we had to literally sit and correct those things the best way possible by ourselves. And we prepared the list. That is the preliminary list at this moment. Now we need to go to each and every sites and to find out the actual latitude, longitude of sites and the current status of that sites. Then you have to update our Excel file of this 1,500 data set, and then if we plot, then we have a database for our Indian subcontinent. Until it will take another 10 years, probably it will take another 10 years for us to do that, but we are slowly progressing. We are doing it one by one. We are taking it up. We are doing it. So keep doing it. That's the only thing what we can do at this moment. So more people joining us in doing that, and we are all also in talk with one of the company in Pune. They are providing us with a mobile application where we can go to the site without having a network, and you can keep the points marked, and it will automatically report into the backend. So it will automatically collect, because most of the time the challenge what you are having in some remote locations where we go for a survey, the mobile network doesn't work. And when you go to sites and when you actually identify the location, GPS location of that, because the mobile network was not there, it may not be a proper one. When you come back and plot it, it will fall somewhere else. So this kind of difficulties we are having. So we are in process of developing an application which can work without mobile network, and it is directly connecting to the satellite and get the latitude, longitude, and will get updated to the system when it is connected to the mobile network or any Wi-Fi network. So that kind of technological things has to come in. Only then our work what we are doing or the work what we are planning to do will get the benefit. So this is GIS. So GIS have basically two things. One is the spatial data and another one is the attribute. Spatial data is what? Like I said, when you capture an image using the mobile phone, it captures the image. There it will show the building or the people or the tree or something, and it will give the latitude, longitude, so that it is already given the latitude, longitude to that image. Now the attributes in that, what is the attributes? Attributes, which person is there in the picture, that is an attribute. How many number of persons are there in the picture, that is an attribute. What other things are there in the picture, whether it's a building, there is a tree, there is a fencing, there is a cycle, there is a car. This all can be an attribute which is connected to one image. So each spatial image what you are connecting can be connected to a n number of attributes. So attributes is nothing but which is the details of that one picture. That when it comes to the location, or when it comes to the GIS platform, this is called the pixel, where I call the picture, that becomes the pixel. What is the pixel? Every image when you open on a GIS platform, that comes with a number of pixels, and that pixels, each pixels have some value, and there would be n number of attribute associated with that pixel. So the system will be only doing an analysis of one pixel to another pixel, then the next pixel, then the next pixel. What is the relation? So system is capable to analyze that in the backend. Okay, so these are the two things which is there in the data. And when you come down to the spatial data, there are two kind of data sets available. One is raster and another one is vector. Raster is nothing but the image what you are capturing, which have pixels, and each pixels will have a value. For example, this is a raster image where all green pixels are given number 1 and 2 given blue. That means when you see this image, with this image in green, because it has given a value of 1. We see that image as blue because we have given a value of 2 to that pixel. And the block which is having 3 will be seen as red. So this is the same image what we see in most of the photographs, mobile photographs when you take. As a result, what happens when you keep on zooming it, after one point we'll say that okay, it's getting pixelized. Why is it getting pixelized? Because when these things are smaller in size, so that size of the pixels are smaller and smaller, and they are closer and closer, and our eyes are not capable to differentiate between that different blocks. But when you zoom it into the depth, when you go more and more zoom, then it gets pixelized. So the images what you are using, for example, if you scan a Indian map or click a picture of the Indian map, put it in the GIS platform, that will become a raster image. You cannot indefinitely zoom into that and identify that. At one point it will get pixelized, we will be able to understand that. Or if you are downloading a topo sheet and using it in the map and it's a JPG image, that is going to be having the same problem. If you are downloading an SRTM image, that is going to having the same problem because that is a raster image. If you are downloading a remote sensing data, and if you are downloading it and using it in the GIS platform, that is again a raster data. It is not vector data, because the remote sensing data, as I said, they will be capturing, each layer will have millions of pixels. Each pixels will have one value, and that one value is the reflectance of that particular wavelength. Okay, so that is the pixels here. So that is the pixelization or the vector, the raster format. But when you come down to the vector format, that have indefinite zooming facility, like what you are doing in the CorelDRAW, or if you are doing it in the Adobe Illustrator, or any graphical designing softwares what you are using. When you draw a line on CorelDRAW and you are zooming in and zooming in and zooming in, it will never end. Why it is not ending? Because the software understands that there is a point, and that point has a coordinate, XY coordinate. So that XY coordinates will never change. As you zoom in and zoom in, it will never change. It will only that kind of making that point with that coordinate. And if you are making a line, it will say that x1 y1 and x2 y2. It will be x1 y1 and x2 y2. It is connected. So if you are zooming in, then the software will be able to connect that, and it will keep on enlarging. It will never disconnect between x1 y1 and x2 y2. So everything works with that, the computation method. It is not the pixel, it's not the block. It is connecting between the numbers or the x and y coordinates. So that becomes the raster. So that becomes the vector. So vector converting to vector from raster is possible in GIS platform. If you have a Indian geographical map, Indian geological map, or in Indian topographical map, you have an image. You can trace those images by using the cursor. You can make points, or you can make lines, or you can make shapes, and you can convert that into a vector format. Or there are processes, some of the things you will be automatically converted into vector by identifying its pattern and line and the points. That also can be done in the system. And the same thing is possible if you have a have a vector, you can convert it back to raster also. Vector to raster, raster to vector, both things are possible in the GIS platform. Sometimes the raster to vector may be some little tedious or time consuming. Otherwise, vector to raster is a easy thing. So that is what I was telling. When you are having the map, I told you now that the Tapi River basin, whether the green shades what you are getting, if I want to find out that wherever the areas where I'm getting the green shade, collect it together, make a polygon, what you are doing is raster to vector. So when that polygon is made, that will become a vector, and then you can play with it. You can calculate the volume, you can area, you can calculate the perimeter, you can measure the diameter, we can measure the length, we can measure anything out of it. You can do all that parameters. But only thing in this platform, the software will be able to identify a point or a area or a line. Three things. It only understands this: point, line, or area or polygon. Nothing else. We don't have any other things in the software. So if you have a point, that will be xy. If you have a line, that will be x1, y1 to x2, y2, or xn, yn, indefinite. And if you have a polygon or an area, so it should be starting from one point and close to another point. So unless and until you don't close, it will consider as a line. When you close it, it will become an area. And these are the common file formats. Every software what we are using will have different formats. They have their what we call, like if you are using QGIS, their raster formats what they are preferring may not be directly openable or useful in the ArcGIS format or in the ArcGIS software, because they want to make their software useful. But there is one common format, very useful for us when we play with different softwares. One is called the shapefile, that the extension is .shp, and another one is called the GeoTIFF, that is for the raster images, and this is for the vector images. Shapefile and the GeoTIFF format. This is TIFF format with geo coordinates. So these two formats what we are very widely using in the studies. So we'll come to this formats and the changes in the details when we do practically in it. Okay, I think at this stage we are understood the concepts of remote sensing and GIS. And GIS, there are a number of softwares available. The free and the best one available in the market is QGIS. Other softwares are also available, Diva GIS. Many free open source softwares are also available. But the QGIS, I personally feel that there are so many people using it, and there are so many developments going on. There are many updates coming up, and they use many people use it. And ArcGIS is the most widely used, but it is a bit expensive. Earlier, the single licenses, they used to give perpetual licenses for the lifetime licenses like 10 lakh, 15 lakhs. But recently, they have started this ArcGIS Pro, and they are coming up with an annual subscription, like personal use. You can get an annual license of ArcGIS with around 10,000 rupees also. You'll get an ArcGIS license. MapInfo and IRIDAS is basically for the remote sensing image processing. That is the dedicated software. ArcGIS, MapInfo, QGIS, MicroStation and AutoCAD Map I have never used. I know that they have something I have never used. I have used ArcGIS, MapInfo, IRIDAS and QGIS, but other things I have never used. And I personally use ArcGIS as the GIS software. And if you want to do a lot of corrections in the remote sensing data and some manipulations in the remote sensing data, this is the image processing software we have to use. Okay, so now coming to the point where if you want to download some data for our studies, so these are the most important resources which are available. So SRTM, this is Digital Elevation Model, Shuttle Radar Topographic Mission, and the best source to download that is Google USGS Earth Explorer. You need to register yourself using a user ID and password, and then you know where to, because they have a pool of database. and you should know that where from you want to download and which part of the earth you want to download the data. You go and download that. And I know there are a number of other sources they claim, and this is having a resolution of 90 meter, and there are 90 meter means you will get an image. There would be one pixel will be of 90 meter size. So that means every 90 by 90 square meters you have one database for the entire region. And there would be people who will be claiming that you have a 20 meter or 30 meter resolution database of SRTM, unless and until they are all done surveys, because SRTM was a global survey done by USGS some years back. And I don't know any time recently they have done this exercise again, because they have done it 90 meter resolution. But now when you get it 90 meter resolution, people are doing some calculations and manipulations to cut this 90 meter into different smaller sizes, and they claim it is a high resolution database of 30 meter or 45 meter or something like that. But I personally prefer the only 90 meter resolution database from USGS. That is the authentic source where we can download 90 meter database and you can use it. And I have done an exercise in some years back. I downloaded the entire Indian subcontinent database and I prepared the complete Indian SRTM map for my personal use. So I don't frequently go to this sites and download again, because now I have the database available with me for Indian subcontinent, and entire India is there, and wherever the regions I want to cut, I just crop that region and use it. Similarly, I did it for the geological map also, because each of these maps, when you download, we all download it into smaller parts. Okay, it won't be coming into one single image for India. So we have to download. And for example, this SRTM, I think around 3200 or 4000, around 4000 tiles were there for India. So we downloaded it step by step, and then we combined everything, merge everything, and make a single map. So we have one single India map right now. Similarly, Landsat, but Landsat I have done that. I haven't done it for India because it's one tile is 1 GB file. So my computers are not now capable to manage more than 2 tiles, because it needs a high resolution, high performing computers to operate that. And TopoSheets is a very beautiful, if you are starting to work on any region, the first before going into SRTM, before going into Landsat, before going to anything, you have to first download the TopoSheet, which is freely available. The PDF can be freely available from the Survey of India website. Go to the website, give your Aadhaar number, do the registration, and find out which part of the India you want the TopoSheet. Select the state, put the city, and see which part you want, and then download that. You will get a beautiful map, 1:50,000 map that is coming in PDF. And if you want a shapefile of that, they are charging around 6,900 rupees per sheet, but I don't recommend that. It is not meant to be needed. And this downloaded PDF, you can convert it into a JPG image, and you can open it in the GIS software and geocode it, and you have the complete geocoded and TopoSheet. That is possible. Okay, so if you are getting a lot of fund from some sources, then I would say that you download everything in the shapefile, download it and use it. But until you are not getting the funding, let us start working with the PDF at this moment, and that is what I also do. So I'll personally take you through these different sites whenever we are working on the remote sensing in practical. So I think that's about the remote sensing, and now we have the GPS. GPS is nothing, I don't want to go anything details about GPS. Only thing I want to say that the handheld GPS techniques what we are using, or what we are usually using, they have a resolution of around 30 meter, and our mobile phones these days are much better than the handheld GPS. Only benefit of using a handheld GPS or a mobile phone is that when you are going to a field which is remote in nature, where there is no mobile network connection, the mobile GPS may not perform better, but that places this GPS will be better. Otherwise, in the resolution point of view, unless and until you are going for a 5 lakh, 6 lakh handheld GPS, you are getting the same receiver or the same accuracy as of your mobile GPS. So that's it. If you are going for a higher end analysis, and if you need a very detailed resolution study or the survey, then differential GPS is a good option. But it's very costly. Single system will come around 25 lakhs to 30 lakhs, but they claim that they are having a resolution of 2 millimeter. So these are the GPS that people uses to identify the millimeter level movement of Indian subcontinent. So there are permanent stations installed, and they are monitoring that how our Indian subcontinent moving, and these are the GPSs they use. So they are costly in nature. This is nothing but they have two systems rather what is having a single sense receiver, because in a handheld mobile there is one single receiver. It is directly connecting to the satellite and the calculation done and identifying the location. But when you are using a differential GPS, we have one receiver which is stable on the surface, and we take another receiver and move around, and when we are moving around, we are not directly in connect with the Landsat. We rather connect it with the stable one, and that is connected with the satellite, and then satellite also connected with the moving receiver. So there are multiple connections, so that reduces the uncertainties between this. So there is at least one point which is close by, and that calculations are more accurate, and then it is corrected with the GPS, and then there are softwares which actually do a lot of corrections in the atmosphere changes during that period, because clouds will make a lot of difference, the pollution will make a lot of differences, because the signals are traveling kilometers from satellites to the receiver. So there are a lot of corrections, and we can make the database more accurate. So that is differential GPS. So I think that's about from my side for today. So I have discussed three main things today. I discussed about GIS and remote sensing, GIS and GPS. And the only objective for today's lecture was to give you a confidence that these things are very easy to use. We only need to understand the fundamental things, and if you understand this conceptual framework at this point of time, please walk through me whenever I post this small task. Okay, whenever I post the small task, just do that, watch that, find some time, and if you are doing it for the entire month, at the end of the month, I'm confident then you will also get a confidence in using that softwares, and you will learn a process of learning yourself these topics, and you will be able to produce some beautiful maps from this.